Good evening, everybody. Thank you, Amy. And welcome to our day 2 plenary and our last plenary for the 2022 RUME. And of course, as you know, it's Dr. Paul Dawkins. And to say some words about Paul, I'm going to invite Kevin up here. Kevin Moore.
Thank you all for joining us on this fine, cold evening out there in Boston. It is with distinct pleasure that I get to introduce Paul Dawkins, who is a near and dear friend of mine, and the most recent winner of the Annie and John Selden Award, which, for those that don't know, is given at most every other year to someone with distinguished scholarship and publication in mathematics education research, specifically within the RUME genre. So let's all congratulate Paul again for that award. All right, so of course, I got to do a little bit of due diligence in terms of talking about Paul's background. So for those that don't know, Paul did his Bachelor of Science in Mathematics at Angelo State University. Of course, it makes sense with a focus also in English and philosophy. I think that resonates with a lot of people if you've had a conversation with him at any point in your life. From there, he moved on to the University of Texas at Arlington, where he worked with Dr. James Alvarez, who I've been fortunate enough to get to know as well. And he completed his dissertation, I believe, in 2009, if my memory serves me right. And then he worked as an instructor there. And then since then has worked for Northern Illinois. Spent a little bit of time at Arizona State, go Sun Devils. And now finds himself at the powerhouse that is Texas State University. Amazing faculty that they've pulled together there. In terms of Paul's productivity, I think you can definitely pull up his Vita and read it yourself. It is impressive. Paul has basically run the gamut in scholarship in terms of publishing in the traditional mathematics education journals. I didn't do an official count to see if he's covered them all, but I do challenge him if he has not. And Paul's been part of several projects. He has a new project coming down the pipeline. Just a really impressive scholar in our field, and at still a pretty young age. In terms of summarizing Paul's work, I think this is probably a fair generalization to make, that it focuses on logic, proof, and content, or some combination of all these if you look at any paper of his. But what has always stood out to me in terms of both reading his papers, following his work, and then several conversations that we have, is that he's always putting students at the center of his work. These are all pulled from titles of his papers that you'll see students throughout many of his titles. Students' interpretation, students' meanings, students. And I think one of the things that's enabled Paul to do that's creative and novel, he's been one of the few people that have really looked seriously at how content pushes logic and proof. How do students' meanings and interpretation of different content areas actually inform their proving processes, as well as the logic that they provide, relative if it's just logic in and of itself or logic relative to the application and use of proof. So fortunately, I get to let Paul talk about his work and what you can learn from his work. So I'm going to stop there relative to his scholarship, because I'm sure he's going to talk to us for a while on that. And I'm going to talk a little bit about what else you can learn from Paul, because I've known Paul since, I think, 2008 or 9. Maryland had invited his advisor out to survey and look at our pathways materials. And James brought along Paul, and then Paul and I don't know why we liked each other right away, but then became dear friends immediately, and we've been with each other ever since then. So I'm going to speak on some of the things I've learned from him, and I think other people in this room have probably learned from him too along that way. So first, square dancing. If you don't know how to square dance, Paul is your man, especially if it's, I cross out nation because Texas really is the nation, at one of their finest establishments. So if you ever find yourself in Fort Worth, go with him and Steph to Billy Bob's. It'll be a wondrous time, I promise. Spoken poetry. It's definitely one of arguably maybe not Paul's strong suit, but you can definitely learn spoken poetry through Paul, especially of your favorite or maybe not so favorite hits after he's done spoken poetry of that. For those that don't get the inside joke there, Indianapolis talent show, which was epic for a lot of different reasons. Paul gave us a rendition from The Little Mermaid as well as Madonna's Express Yourself, was it? Yes. So feel free to ask him to give us a rendition of that later tonight. Other things you can learn from Paul, keeping someone up talking till 3 a.m. Pretty common conference experience. If you go out with Paul or you room with him, plan on being up till 3 a.m., even if you don't want to be. Some of my favorite experiences with Paul is literally being mid-conversation as his roommate, and he falls asleep on you at like 2:45 or something like that. Like you're literally in mid-conversation, you say something back, and then you get nothing back. You look over, he's sitting up asleep. So, what else? Let's see what I don't even remember what all I put in there. Oh, wearing the same T-shirt 5 years straight. This is actually not I don't think a well-known fact of Paul. Was this undergrad right around that time? Yeah, high school undergrad. Paul was able to wear the same shirt for 5 years straight. I embellished a little bit. It was just 5 days a week. He took weekends off, and he had a couple shirts in the rotation, but it was always a Cheddar's Scratch Kitchen shirt. So if you're paring down your wardrobe and you really want to know how to be efficient with it, Paul, talk to Paul. Taking liberties with talk time slots, definitely something you can learn from Paul. Gets down, questions. Oh wait, there's no time for questions. So, sharing food, beer, fun, and good company. I think this is something like we can all learn from Paul, right? Like if you're going to be around Paul after this talk, I bet all of these are going to be involved, right? You're going to have some good food, you're going to have some good beer, you're going to have fun, and you're going to be around good people. You can always trust that with Paul when you're with him. And it's on this last point that I'd like to say a little bit more about what you can learn from Paul too. We can learn about caring from Paul. Paul cares, right? That's one of the strongest quality or strongest personality traits of him. He cares about the field, right? If you ever talk to Paul, he engages authentically with you, no matter who you are, what you do, how long you've been in the field, right? Your background doesn't matter, your research focus doesn't matter. He engages authentically with you. He cares about quality, right? When he engages with you, it's not at a surface level. It's deep. It's meaningful. He takes his time, right? He gives you careful feedback. He considers what you're saying and really thinks hard about it and connects with you so the relationship is meaningful, so there's quality to it. Most importantly, he cares about us. He cares about us as people, right? That's why he stays up with us till 3 a.m., right? It's not, you don't have just random, like artificial, professional conversations with Paul till 3 a.m. You actually have serious conversations about you, about life, about whatever's interesting to you, whether it be religion or sports or your relationship, right? Paul shows that he cares by engaging with you, by talking with you, by connecting with you, and being there for you no matter how late it takes you and no matter how tired you might actually be. So when I think about this, and like one of the things we can learn from Paul, I think not only can we learn about the type of colleague that we should be, but we learn about the type of person we should be with each other, right? So you're going to learn a lot from Paul's talk, but I think one of the things we should all take away tonight is not only the type of scholar he is, but the type of person he is. So on that note, Paul, we look forward to hearing your talk tonight.
Thanks, friends. Thank you, Kevin, especially. But I just want to say, RUME, this community just means so very much to me. Just terribly important to me. This has been my intellectual home, and this is where I've learned how to be a scholar. I feel like even when I don't get to be here for a year or maybe 2 years, I still feel like I've been around y'all because y'all are my mental interlocutors when I am doing my work at home. You are the people that mentally I feel like I'm engaging with. I'm so thankful for this community. I'm thankful for the culture that we have, and the supportive attitude we have. And so for that, it's just beyond an honor to get to share tonight. But without any more words, I want to talk about some math ed. That was way too much talking about me. So if anybody's been following my work, I do have probably an unhealthy preoccupation with logic. So I'm going to talk to you a little bit about that tonight. And hopefully share some just insights I've gained from talking with students and trying to understand how language works for them and how we can hopefully make logic work for them in more productive ways. Let me see if this is gonna, is there some trick here I ought to be doing on advancing that? I've got something, but it's not advancing. So first, I want to thank a lot of folks who've worked with me on various parts of this project. I've been studying logic since I guess about 2014 was when I really started focusing on logic specifically, but some of the data that I'm going to show today is even older than that. But thank you so much to all these people. Especially, I want to mention Kyung-Ha Roh, who's been really one of my longest standing and closest collaborators and from whom and with whom I've learned so much. But another theme I want to have throughout this talk is giving thanks to those who've taught me, and by that I want to refer specifically to the students who have given me their time and who have taught me a lot about their reasoning. And so I want to acknowledge them as their many contributions to what it is that I get to do. It's amazing that this gets to be my job. I'm still astounded, and I'm thankful for students contributing to that. So I want to share some stories about how students have taught me about how mathematical language works for them. I'm going to try to kind of convey it in 3 major episodes, but really give you one big idea. And so we'll look at a student proving or students proving, students comparing statements, students comparing proofs. But the TLDR, right, too long didn't read or stopped listening, is that student language use, in my experience, is very largely coherent. It's very rational, but it's just distinct from mathematical language use. And mathematical language really works in some kind of non-obvious ways that we need to help students make sense of and we need to kind of invite them into. So I'd like to give some ideas about that. So I want to start with a story. Thanks to Kevin, I was a part of the STAR program many years ago. So in 2012, I got to go spend a week at Park City Math Institute. And I very distinctly remember we were on a break. We were in the hotel room just resting. And I was so impressed with a lot of the work that I saw Kevin doing and Pat Thompson doing, exploring students' meanings for graphs. And I wanted to kind of apply that within the proof-based setting in which I was working. And so I got this question: what are students' meanings for conditional statements? And so this question compelled me, so I thought I'm going to go home and work on this. Now, a confession I should make here is that I was just terribly ignorant at the time of how old that question was and how much had been done on it that I was really unaware of, specifically in philosophy and cognitive science. Since then, I've tried to learn a lot. But then again, can we really know our own ignorance? I feel like there's probably a contradiction in that. So I'd like to think I'm a little less so. But without that, I'm not going to survey a whole lot about what came out, partially because I kind of just dove in without knowing a whole lot of the background literature at the time. So here's what ended up happening. I went home, and one of my colleagues was teaching an axiomatic geometry course and was very kind to let me come and interview some of his students. So I recruited a couple of students, and I was doing task-based interviews, and they were working on the proof. The task in general was Euclid's fifth postulate, if and only if Playfair's postulate, but specifically students were working on proving Euclid's fifth implies Playfair's. And so these are the statements of those two statements, the expressions of those two statements from their book. So Euclid's fifth says in these transversal configurations, if the same side interior angles sum to less than 180, then the lines intersect on that side. So that's the diagram again from their textbook about what that meant. And Playfair says if you have a line and a point not on the line, there's exactly one parallel through that point to the given line. Okay, there's also this auxiliary statement, theorem star, given two lines cut by transversal. If the same side interiors sum to 180, then the lines do not intersect. So with that, there's conditionals all over this, right? Euclid's fifth is a conditional, theorem star is a conditional, Playfair's can kind of be rendered as a conditional if you want, and we're proving one of these implies the other, so that's another if-then, or two of them. Lots of conditionals. So this seemed like a great place to explore what are students' meanings for conditionals. So I was working with two students whom I call Kirk and Oren, and in particular, Kirk taught me how misleading my question already was in the way I was thinking about it. In terms of the work of understanding his mathematics. And for this, I'm so thankful to Kirk for teaching me. So let me kind of give you an account of how Kirk was reasoning about proving that Euclid's fifth implied Playfair's. He classified all the angle sums, alpha plus beta, in the arrangement that you see here. He said if the angle sum is less than 180, then the lines meet on that side. If the angle sum is greater than 180, then the angle sum on the other side is less than 180 and the lines meet on the other side. And if the sum is 180, then by that theorem star thing, we know the lines don't meet. So that's good. 7 different times then in the conversation, Kirk explained how this proved Playfair's because there's only one instance where the lines don't meet. Here's a kind of extended quote of him thinking, if the angles add to 180 exactly, then the lines will not meet. And it's like only one instance where the lines will not meet. So basically, there's only one time where the lines will not meet. And Playfair's postulate basically states there's only one instance or case where the lines will not meet. So they kind of like either way, there's only one case. And when I says either way, I think part of what he's thinking there is either way meaning Euclid's fifth or Playfair's. So let me unpack what I think is going on here and put it in contrast to the way we tend to think about conditionals working in mathematics. Something like a direct proof of an implication is often assumed to have some kind of path from hypotheses to conclusions. We parse it into an if and a then, and we go from the if to the then. And so therefore, we might want to go from Euclid's fifth to Playfair's. And I kind of anticipated student reasoning might match that. Oren, Kirk's partner, in fact, did want to do that. He was really working on saying, how do we get from Euclid's to Playfair's? And there was a lot of, not like tension, but there was a lot of kind of dissonance between the two students as they talked, because Oren felt very dissatisfied with what Kirk had so far argued, and Kirk really thought they were done and was unsure why Oren wanted to move on. And so let me try to say what I think was going on for Kirk was he said, look, Euclid's fifth says there's only one instance of parallel. Playfair's says there's only one instance of parallel. They say the same thing, so they're equivalent. They say the same thing. So does that make sense? So to kind of portray that, both of these statements aren't pointing at each other. These statements are both pointing at the line arrangements. And what they both say about the line arrangements is the same. They both say there's only one instance. Therefore, Euclid's fifth and Playfair's imply each other or whatever. So, key insight. We're going to return to this. For students, at least some students, I don't want to overstate this too much, but for many students, mathematical statements refer to states of affairs. Stated as such, it's a little trite, but does everybody see the point? The two statements don't point at each other. They point to states of affairs, meaning the lines that they're talking about. They're talking about geometry. They're talking about line arrangements. Okay, so let's just kind of reflect a little bit on that, but we'll have time to unpack that idea over the course of the talk. So some studies of students' logical reasoning claim that students interpret conditionals as biconditionals. Well, what's going on there? This is sort of, when we say that they interpret them like biconditionals, that's sort of saying that statements are somehow truth functional. There's truth values to the two parts, and there's a truth value to the whole thing that depends on the parts. And the way students are using it matches the way truth values work for biconditionals, not the way for conditionals. But I would claim that that imposes a lot on students that may or may not be present in their reasoning. In fact, I would claim this, especially for Kirk, would impose something foreign. If you look at his various articulations about these relationships, notice in Euclid's fifth, he said, Euclid's fifth is that these angles are less than 180 and they would meet on that side. So notice now it's not if, then, it's and. In another case, he quotes theorem star and he says that angle beta plus alpha has to equal 180 if it's parallel. That would technically be the converse of theorem star if he was thinking directionally. But I think what's going on is if Kirk is really just imagining these line arrangements, then angle sums being 180 and parallelism just co-occur. They either both happen or they both don't. And there's no inherent direction between how one or the other happens or doesn't happen. Does that make sense? And so this is why at various points Kirk says if then, and, or, he's alternating this language because for him there's not some directed relationship between them. So based on that idea, then, it made me realize, I think we should be challenged by that just a touch. Let me stop for one moment on that. In what way do we want students to think that there is a directed relationship between the angle sum and the parallelness of the lines? Like, if they're just imagining these line arrangements, in what sense is there actually a direction between that relationship? We often talk about it in terms of this like epistemic language of like the unfolding of knowledge. If I know the angle sum is 180, then I also know or can conclude the lines intersect or something like that. But that's weird. That doesn't just describe what's happening on the ground. That's something we kind of impose on our way of thinking about the situation. And so I think it's actually quite coherent the way Kirk is reasoning about it. And so how would we push or encourage a student like Kirk to adopt some kind of directed relationship in that way? Okay, so I then started with a new question. Kirk convinced me I needed a new question. So how can students construct the mathematical meaning of conditionals? How can I sort of create a space in which they would do that? So here was kind of an insight that I had, what are the origins of logic? I would claim that some of the beginnings of logic are not sort of going to the abstract, any statement of the form if P then Q. Often we start by comparing close correlates. And so I pulled a few like arguments offline in various settings to just portray this idea that you can tell somebody is engaging in a type of logical activity when they compare two claims or two arguments, and by saying, look, these two specific arguments have the same structure because they are parallel, they probably should have shared properties, and if you don't like one of these arguments, you probably shouldn't like the other. So you'll notice this language of by the same argument, or that is like saying. So one example, you may think there's no point in singing unless you're good at it, but that is like saying there's no point in doing anything unless you're particularly gifted at it, which is ridiculous. So if you don't buy the second, you shouldn't buy the first, right? These two hang together. When someone says you shouldn't be sad because someone has it worse than you, that's like saying you shouldn't be happy because someone has it better than you. So they're setting up an analogy between two things that have a shared structure and saying because they have the same structure, that maybe they have the same properties. So I wanted to kind of say, well, if that's the seeds of logic, how could we begin to engage students in using close comparisons to construct logical insights or logical ideas? So I said, well, what if we give students lots of statements, mathematical statements that have the same form, maybe or if then. So I started, probably can't read that, but this is a whole list of or statements that I started giving to students and having them read them, encouraging them to compare how they read them to see if they could sort of systematize to where they start to read all of these or statements in somewhat similar ways. But this gave me a lot of insight along the way into how do these statements read to students and why. So let me talk a little bit then, again, questioning my assumptions about how these statements actually aren't as parallel as I thought they were for students. And there's actually very good reasons why. So again, thank you to pseudonyms, Eric, Ovid, Mandy, Aaron, and Lionel, a bunch of students who over a few years taught me a lot of new insights here. So let's talk about this. How are quantified and non-quantified claims related? Mathematically, if you look at A1 and A2, they should, mathematically, we'd think they're in a pretty close relationship. A2 is an instance of A1, so if A1 is true, we would think A2 ought to be true mathematically. But it's actually quite common that students will say A1 is true and A2 is false. Why would they say that? Well, by talking with them for a while, basically I've learned this. The or in A1 is kind of necessary. You can't express that relationship without that or. But the A2, the or in A2 is pretty superfluous. I mean, you'd only ever write A2 if you're teaching a logic section. I mean, nobody would say that in another setting. And so what students look at that is they say, well, I would rather say 15 is odd. And to some extent, often people say, oh yeah, well, or students have trouble with or because the whole inclusive and exclusive or thing. And it's like, well, actually, that's not what's going on here. For students, or often expresses alternatives or possibilities. So if you look at A1, as x varies, both x is even or x is odd, both of those are possibilities. They're both sometimes true and they're alternative to each other. Whereas when you say 15 is even or 15 is odd, that doesn't apply. They're not both alternative possibilities. One is in fact the case and the other's not. Once again, student language use. For students, language refers to states of affairs. And we know about 15, it's odd. Okay. Negative claims, it turns out, are pretty weird. Here's four of the statements I like to give to students. They're all about shapes, and they all have a knot somewhere in them. And it turns out that when you say something like, it is not acute, that sort of works differently for students. It plays differently for them than it does for us. In part, I would say that all these statements with knots in them may or may not have the same logical structure as A1. In part because when I say not acute, students often read that as sort of like negating the element of sense, like I'm saying that what you're not a part of. I'm saying you're not in the group we call acute triangles, rather than saying you are in the group of things we call the not acute triangles. Not acute is not a property of triangles. It's a non-property. We lack a property. It's saying something negative. And so for students, that's actually a little bit needs more work. It invites more reasoning. So they often think, if X is not in the acute triangles, then where is it? What can I say about it? That feels sort of unfinished or in need of unpacking. And that's not, it's fine, but what it means is that in fact these other statements don't have quite the same logical structure as A1. And so if we want students to sort of see them as the same, that's something that students have to construct. So to kind of capture some of the insights that I gained as I worked with students on this stuff, I put forth this concept I called students' pronominal sense of reference. That sounds very pretentious. What does that mean? Pronominal means like a pronoun. A pronoun, when I say that or it, I just am pointing at it, right? And in a sense, I think for a lot of students, when they read a lot of the mathematical statements we give them, that sentence points at the things that it refers to, right? In fact, Dubinsky and Yiparaki has said this, I think, quite in a lovely way in that quite well-known paper they did on quantifiers, where they said it's like the statement was a window and students looked through the window at kind of the mathematical world or at whatever the state of affairs, but they didn't see the window. They weren't looking at the sentence. They weren't looking at the language because the language pointed beyond itself to states of affairs. And so specifically then, what I've kind of claimed is when you say is a rectangle, that simply points only to rectangles. Well, again, when I say it that way, it sounds a little trite. Why is that a problem? Well, here's where we often begin teaching logic. Is we begin by saying, no, every statement like that has a truth value, and that truth value could either be true or false. Well, I mean, that's not like it's not a weird thing to say, but again, if students really think, no, the phrase in language refers to the things that make it true, then already we're not starting where students are starting. At least if we give them meaningful sentences, truth tables don't quite capture what's going on for students there. So I'll just say, I'll take one more pot shot at truth tables because I kind of have my grudges against them. According to truth tables, did y'all know this? P implies Q, or P implies Q, or Q implies P is a tautology. It's always true, no matter what P and Q are. Now, do you believe that? As a mathematical statement, do you believe P implies Q or Q implies P is a tautology? It's always true for any value of P and Q. I hope you're saying no, right? So I'll give you an instance. If a triangle is isosceles, then it is right. if a triangle is right, then it's isosceles. Both of those are false statements. But truth tables tell us that that is a tautology. So I think that ought to tell us that truth tables aren't even capturing the way we use mathematical language. And I can give you an explanation as to what's happening there in terms of quantification, but I don't want to detract too far, but I just want to put that potshot out there. I think truth tables are problematic. Okay, let's move. I want to talk more about, well, what could we do that was more productive? So here I'm going to shift into talking about, okay, so I learned all these lessons from kind of the way that language works for students. So then I wanted to really talk about, well, how do we then help students attend to their own language use, to their peers' language use, and helping them just begin to think about language and think about logic to advance their ways of using language and to build logical ideas. So here's a false statement. And an interesting thing that happens when you give students a false statement like this is they know that it's false by a counterexample. And they'll say 15 is a counterexample. And you say, why is 15 a counterexample? And they'll say, because it's a multiple of 3, but not a multiple of 6. And if you are a teacher who's kind of thinking, oh, we're moving towards logic, you hear that and you think, oh, great, they know the negation, right? Because that's like P and not Q. They get it. They already know that. But I found that when you talk to students, they're not, it's almost like as soon as they say that about 15, they can't go back and then like reflect on that articulation they just gave. Because they aren't focused on anything is a counterexample because it's a multiple of 3 and not a multiple of 15, or sorry, and not a multiple of 6. They were simply pointing out to you, what do I know about 15 that makes the statement false? It again refers to the state of affairs. They're describing the number. And so it takes some work for them to go back and be like, okay, so stop, replay what you just said, and let's think about it, to kind of generalize and say, actually, you just gave a sufficient condition, or a necessary condition for any counterexample. If anything is both a multiple of 3 and not a multiple of 6, then that number will always be a counterexample to that statement. That's exactly what every counterexample shares. So if we sort of just quantify that description they give of a counterexample, then they can formulate then what we might call the set of numbers, the set of counterexamples. And then from that, I think we can push them to then engage in this activity of writing what we call a negation, which is a new statement. Now, the distinction here is that the negation is another statement. A counterexample for students is a much more kind of familiar relationship between a statement and objects that it points to. The idea of negating is to relate a statement to another statement. And I've just found that to be a little bit less of a familiar relationship for students, but it's one that's totally within their reach. But I think this is a way to kind of build towards this idea of stating this opposing statement from where they understand of counterexamples. And I'll just show that there's kind of a neat adaptation of this is then once they've formulated the set of counterexamples, you can invite them to do something they find a little curious at first and say, well, okay, now look at a true statement and describe the set of counterexamples or describe the necessary conditions to find a counterexample. And initially what students say is, well, there are none. And you say, yes, that's true. Keep going. But, mirror what you just did here and do it again. And you can say, okay, well, if I wanted a counterexample to this true statement, I would need something that is a multiple of 6 and not a multiple of 3. And actually, this sort of reinvents proof by contradiction in this context. But in the way that David Yopp has referred to as eliminating counterexamples, you argue why can nothing both be is a multiple of 6 and not a multiple of 3? And if, in fact, nothing can do both of those things, then there are no counterexamples. Therefore, it's always true. Another thing that comes out that's really cool is, in fact, students can begin to see a symmetry between saying, if it's a multiple of 6, then it is a multiple of 3. So a direct proof shows there's no counterexamples because nothing with the first condition meets the second. But proof by contraposition says we'll start with the second condition. If you're not a multiple of 3, can you possibly be a multiple of 6? And by proving if you're not a multiple of 3, then you're not a multiple of 6, shows that anything in the second condition can't meet the first. So once again, there's no counterexamples. There's actually beautiful symmetry between the direct proof and contraposition under this viewpoint. But okay, so all of that is just stuff students can build out of something that's actually quite familiar to them, stating counterexample conditions. So let's kind of put together then a few big ideas about this part in terms of advancing students' reasoning as they reflect on their language use. So students understand counterexamples as a relationship between a statement and a referent object. Ideas like negation or implication are relationships between different statements. And we just need to treat that as a little bit less familiar, a little more sophisticated. Students can totally do it, but we just need to find good ways to advance them into those kinds of activities. Furthermore, there's a really big thing here about using language like if, then, and for some. Students will spontaneously use that language quite often. That does not mean that they have systematic ways to think about all such statements. Thinking about every statement of that type is a very strange and kind of esoteric activity. How many of you, while just speaking in the everyday, stop, parse your sentence, abstract the grammatical structure, and then think, what would be true of any statement with that same grammatical structure? It's like, I mean, nobody does that. This is ridiculous, right? And we shouldn't expect that students have engaged in that activity. That's a very, it's not that they can't, but we need to invite them into that opportunity. Students may draw on language to describe states of affairs, and again, they're not always generalizing to all such things, and that's just a really hard thing to do. So to teach logic, I have kind of come to the conclusion that we must invite students to think about and compare the structure of statements, how they refer to objects. I was mentioning today, often we really use truth values to stand in for actually referring to any objects. When we say, is a multiple of 6 is true, that's just a proxy for saying, I'm talking about one of the multiples of 6. And so we use truth values to basically erase reference. And yet reference is what language does for students. And so again, truth values just don't start where students begin. And so I think we can find much better options of how to engage them in logic. Okay, so let's build to yet another question then. So my original question, what are students' meanings for conditional statements? Kirk helped me to kind of doesn't mean, the way I took it to mean it was not as productive. Also, that I learned a lot from the cognitive science about that. How can students construct the meaning of the mathematical meaning of conditionals? This was still the idea of how can I kind of get them on board with the normative mathematics. And again, students helped me to see how many ways that actually the logic that we try to teach really is incompatible in some fundamental ways with the way language works for students. And so really maybe it's kind of unproductive and unnecessary. So then I sort of moved on to a new question of how can we really remake the mathematical meanings of language and logic to be more compatible with students' sense of how language works. Let's just remake the math to kind of meet students a little bit more where they are. So I want to talk a little bit about that, but there's some real challenges here. So final episode about proving. I have no idea where I'm at on time. I should probably check that. Okay. So here's what we did. We started inviting students. Previously, we had students compare statements of the same form. Now we're going to invite students to compare various proofs related to one so they have one theorem and several proofs related to the theorem, but not all the proofs actually prove the theorem. And we wanted students to look at each proof and decide, does this proof prove the theorem? Why or why not? And often we ask a follow-up, if it doesn't prove the theorem, what does it prove? Okay, you can't read all this, but here's the main point you should know. The theorem on the left is if x is a multiple of 6, then it's a multiple of 3. This is a classic conditional theorem whose converse is false. There's a direct proof, a disproof of its converse by counterexample, and then a proof by contrapositive. It's not a particularly pretty proof by contrapositive, but it's a proof by contrapositive. So proof 1 and proof 3 both prove. Proof 2 does not. Then theorem 2 is a biconditional theorem, but I only stated it in conditional form. So if x is a multiple of 2 and a multiple of 7, then it's a multiple of 14. That is a true conditional theorem with a true converse. And in this case, then, there is a direct proof of the theorem and a direct proof of its converse. So proof 2.1 does prove because it's a direct proof. Normatively, we would say proof 2.2 does not prove because it proves the converse. And there's this question of, we wondered about both. Can students kind of come around to seeing some reason why a contrapositive proof would in fact prove the theorem? And any kind of justification for themselves of why a converse proof wouldn't prove the theorem. And if we think about Kirk's reasoning, again, we might understand that when students see sort of a sameness between the two things being related, it's hard to impose a meaningful direction on that, right? So for Kirk, when Euclid's fifth and Playfair's postulate describe the same state of affairs, it's really hard for him to see that there was some direction between those two that was up front, or why there's like two one-directional links between them, because they were just the same. And so we wanted to know, can students construct a kind of coherent reason why the converse proof doesn't prove, and possibly might they do it by comparing it to theorems whose converse is false. So if there's an analogy between these two theorems, would that in fact convince them that because proof 1.2 doesn't prove, proof 2.2 shouldn't prove? And just to be clear about this, if you look in a common intro to proof textbook that, I don't think is a bad textbook. I assigned it to my class some this semester. This is exactly what the book says. Therefore, the meanings, because here is an instance of a conditional theorem whose converse is false, or a conditional statement whose converse is false, because this theorem has a false converse. In general, the meaning of P implies Q and Q implies P are just generally quite different. Because in this instance, they're different, they're always different. I sometimes read to my kids Peppa Pig books, and they have these terrible cases of just gross overgeneralization. They often say things like, Peppa loves dancing, everyone loves dancing. And you're just like, wait a second, that was quite a leap, But this is exactly what Hammack is doing, right? So Peppa's converse isn't the same, and so nobody's converse is the same. I don't know. Okay. But why? So are students going to be convinced by this argument? So we set up this task. That's the laser. We set up this task where they're going to see a statement with its converse that isn't equivalent. Is that going to say anything to them about proof 2.2? We upped the ante a little bit. Here's what we then did next. We modified theorem 2 by changing the numbers 2, 7, and 14 all throughout those two proofs to 4, 6, and 24. Now, what this does is that maybe students don't think the analogy between theorem 1 and theorem 2 is tight enough. So here, literally, all we've done is change the numbers. Everything else is the same. So if you want analogies between theorems and proofs, this is as close of an analogy as you can get. And the question is, do students think that that analogy says anything? Because in this case, theorem 2 prime is false. Proof 2.1 prime is invalid, but proof 2.2 does still work. And so we'll kind of think about this. So April and Mariah were two just absolutely wonderful and delightful participants I had. They were so much fun. Thank you to April and Mariah. They had different views between the two of them about whether proof 2.2 proved theorem 2. So before I changed the numbers. April, in her ways of writing down what does the if and the then part of the theorem mean, here's what she wrote. Multiple of 2 and 7, she wrote 2 times 7 times k. And multiple of 14, she wrote 14 times k. So I hope you'll not find it surprising then that she saw a very strong sameness between these two claims, right? And so unsurprisingly, she had a hard time distinguishing theorem 2 from its converse. They really hung together for her. And so she said proof 2.2 does prove the theorem. It proves the converse and it proves the theorem. On the other hand, Mariah, her partner, they were both computer science majors. Mariah was interpreting the proof in terms of writing code that would actually test these divisibility claims. And so for Mariah, is a multiple of 2 and is a multiple of 7 was like this nested loop thing. And multiple of 14 was a single loop that she was testing. And so for her, these were two, she knew that the same numbers satisfied both. But she did see them as distinct things, and she did say, no, I think the order matters, and so the proof 2.2 doesn't prove. But I want to talk a little bit about April's reasoning. So we were coming back around after we had introduced the modified theorem, so the primes. We then were summarizing what we had observed, and this diagram was what was on the board as we were summarizing. So blue arrows correspond to Mariah's thinking, and green arrows correspond to April's thinking. So they both said proof 2.1 proves theorem 2, proof 2.2 proves the converse, but April did think that proof 2.2 proved theorem 2. They both agreed proof 2.1 prime was invalid, and on and on. And so they both agreed pretty standard interpretation of the two primes. So let's think about, here's the analogy. I'm trying to kind of set up this comparison. What will April say? So as I drew that diagonal green line, I said, now last time you also believed this. She said, yes, I still do. You still do? Good, okay. Just because of how the numbers are. Just because of how the numbers are, okay. But switching it up, putting other numbers in, then you end up with a new theorem. Then no. So what's April saying? April's saying when the numbers are 2, 7, and 14, one thing happens. When the numbers are 4, 6, and 24, a different thing happens. And that's okay. And then she confirmed, she said, I see how this works. Like she pointed at the board and said, I see the analogy you're making, but that doesn't convince me that proof 2.2 does not prove the theorem 2. So here's my take on what's going on for April. Theorem 1 and the converse of 2 prime are both a particular kind of situation. They're a conditional situation where the converse is false, and in those situations, converses don't prove. On the other hand, there are other situations like theorem 2 that are we would call biconditional. In those cases, converses do prove. They're different states of affairs, they're different situations, and the rules of how proofs work in one don't have to affect the rules of how proofs work in the other. Key insight. For students, mathematical statements and proofs refer to states of affairs. And so this like high-level analogy that just because things work this way in one proof about one situation with one set of numbers does not, for students, imply that all the other states of affairs with all the other pairs of numbers ought to work the same. And why, and how would you argue to April that they should? So this is a really interesting thing of like, how do you coherently and productively address that? So this is a big challenge we faced and still face in being honest to April's reasoning here. So logic, by replacing mathematical content with truth values, I think does a lot to misconstrue how language works for students. So I hope I've conveyed that in various ways. I think, though, logic doesn't need to be so incompatible with student language use, and I think we invite students, help them to advance their language use by helping them to reflect on their language use, compare their language across parallel statements, across parallel proofs, and helping them to kind of work on that together. Logic simply just starts off assuming that all statements and arguments of the same form share certain properties. And I just want to say, it's not that I think April couldn't be convinced of that, but just we can't assume that students come in with that assumption. And we need to be honest to find coherent ways to help students recognize that that is kind of an assumption we're making, or that it's actually we have compelling reasons why that should be the case, and try to help them understand why that's a good and useful way to think about language and proofs. And ultimately, what I'll just say is, again, logic answers questions students haven't asked yet. And I think one of the biggest things for me is just what I love about April's reasoning is April understood the question quite deeply. Her answer wasn't the same one that maybe I wanted, but I'm proud that she saw the analogy, right? And I think even that was just a lot of progress in the design work that I want to do in helping her to recognize the question and to be able to kind of think for herself about what makes sense to me here. Okay, so I'll end here with just sharing a little bit about some instructional engineering efforts that we've been working on here largely with Kyung-Ha Roh. So again, just so much thanks to Kyung-Ha for her partnership in this. And so what we're trying to help students think about is this, especially with this idea of converse independence, that converse statements are related but different. They're distinct and they don't imply each other. We want to help students think about how mathematical statements both have a very systematic way of referring to states of affairs, but also there's a built-in ambiguity. And what I mean by that is a conditional statement always refers to a subset relation. So if a conditional statement's true, it conveys a subset relation between truth sets, meaning the set of things with property P is a subset of the set of things with property Q. But it also always entails an ambiguity, because there's always two different ways I can have a subset relation. I can kind of have a subset that's a proper subset, or a subset that also exhausts the superset. And then what we need to think about is then anytime I affirm a conditional statement, then the next question I want to ask is, how do I disambiguate which of the two situations I'm in? And how do I do that? Well, I ask the converse question, right? The converse, because it also systematically refers to two possible states of affairs, but again, has its own ambiguities. But by comparing the various statements, we gain more insight and can be more specific. And so it's interesting to think about how what often happens for students is, if a theorem is if and only if, they want to say not the one condition, one direction or the other, they want to say both, right? If you know two things are equal, why would you say they're unequal or equal? Why would you do that? Well, so we need to give them a coherent reason why that sort of constructing a sameness as two one-directed relationships, why is that useful and productive? And in fact, what's really interesting is the most coherent reason why we do that is because it works for proving. But what's the problem? We teach logic before they're doing proving, so they don't know why it's useful, right? They don't know why that's a coherent. The reason why it makes sense only comes later. And so then I think by having them explore how statements refer, we can still build a really nice way to think about that even before we get to proofs. So then I want to kind of give, at the end of a teaching sequence we've been working on, I want to give you a picture of then how we're trying to engage students really productively in again, thinking about these systematic ways that language works, trying to generalize, trying to abstract, but also attending to both to arbitrariness or kind of to ambiguity in mathematical language at the same time. So this is at the end of a long sequence where we've been doing stuff with a lot of specific theorems and comparing a bunch of proofs. This is a task that we've been giving. So imagine we're considering now two mystery properties P and Q. So I'm not telling you what P and Q are, they're just properties. And everything in this set S either has P or doesn't have P, everything has Q or doesn't have Q. Now imagine somebody writes a proof of this type. Let X not have property Q, and by some sequence of steps they conclude thus X does not have property P. What are the possible relationships between the truth sets of P and Q? Now, since this is a proof of the contrapositive of, so if anything, you could say specifically what it proves is Q complement is a subset of P complement. But that, by contraposition, or just by kind of reasoning about it, entails then that P is a subset of Q. But there's still some ambiguity there. It may be that Q complement is equal to P complement, or it may be a proper subset. And so we need to think about, there's at least two diagrams we ought to draw there, and maybe even more diagrams depending on how they want to deal with the complement structure. What kind of proofs could be written to more precisely specify the relationship between the truth sets? So if you want to pick which of the diagrams is most accurate, what else would you want to know? So there's still an ambiguity here, so we want them to represent the ambiguity, specify how would I resolve the ambiguity, and then finally, after they've mapped from this proof to a set relation, maybe in a diagrammatic setting, we want them to map back now to language. And so we say, write down two statements that must be true based on this proof, two statements that must be false based on this proof, and two statements that we can't yet determine if they're true or false based only on this proof. And so I hope this gives you a picture of how we're really trying to play on how is this more honest to where students start. First off, we're talking about properties that objects have, and the properties refer to objects. We don't just talk about true and false. We talk about the sets of things that make them true. But we're after comparing a whole bunch of these various ones, we do want them to kind of abstract and think about there's all these various possibilities for P and Q, and based on those possibilities, what do we know and what's still ambiguous? And it sort of builds into thinking about arbitrariness, ambiguity, all these sorts of key logical ideas, I think. So final note, just if nothing else on a practical note, breaking up an equivalence into two one-directed relationship is just strange. We need to treat that as like less obvious than we feel like it is. But I think there are really coherent ways to invite students into it. I'll end with that. I'll say, if I can just say sort of on a final personal note, I'll just say I want to give thanks for and to, I guess, my father-in-law who died this December. I'm actually, this shirt is a shirt of his, and so I just do want to give thanks to him. And on a personal note, I feel like I must give thanks to Jesus Christ, who is my dignity and my delight, and without whom I think the last 2 years for me would have been a lot more unbearable. So with that, thank you so much for your time. I really appreciate it. How did I do on time? I know I get picked on.
I think you were good, Paul.
No, I wanted, was that like under an hour? I'll take it. Kevin took a long time. He went on and on about me. Okay.
So I'm going to try with some help from Nick, I think. Well, with Stray. So Stray will sort of go for the questions in room, and if we have virtual questions, they'll either speak up that we will hear, or I will read their questions out. So I want to open it up for some questions, either in person or virtual.
Hi, Paul.
Hey, Sean.
Hey, thanks so much for the talk. I really was happy when you started getting into episode 3. I mean, there was a little joy in my heart when I heard you say, I'm just going to paraphrase, make mathematics meaningful for the students. I don't think I said it exactly right, but it's so hard for so many of us to try to rethink of making mathematics. And I see your state of affairs concepts as a way in which it probably helped you transition, but I'd love to hear more about your journey. So could you share a little about how the state of affairs connected you maybe more to how you started to look at equity and access for students to gain this knowledge of logic and proof? How did you change to that idea of to make mathematics for the students?
Yeah, well, so I was very inspired early on by realistic mathematics education, and I was thinking, hey, if I wanted students to reinvent logic, what would be sort of the raw, what would be the experientially real activity in which I could engage them, out of which they would construct this? And that's where I really came to that idea of just comparing different statements and saying, how are they the same? And so I started with just reading activity, deciding if it's true or false, and trying to compare across these. And again, so one of the pairs that I didn't really talk a lot about, but I mentioned, is Aaron and Lionel. In particular, they, after some other students had come in and just spent long periods of time wrestling over some of these or statements and trying to get a grip on how to determine whether they were true or false, Aaron and Lionel just ripped through them. And part of what I really noticed in their activity was they associated each of these properties, the set of all the things that make it true or make it false or whatever. So an instance is like Aaron, when reasoning about the phrase is not equilateral, she would say things like, well, equilateral, that's really specific, so this is almost everything. Like, since equilateral triangles are this very kind of particular group, when you say not equilateral, that covers everything else. And that consistent attention to the set of objects that make true. So a lot of other students think about objects that make true, but they didn't think about sets of objects that made true. And it was so clear, the contrast was so stark in terms of how Aaron and Lionel were able to reason about these tasks, that was a seed that I just took from them to say, maybe I can nudge students into that kind of reasoning. And it really led me to this idea of saying, well, what is the same between different conditional statements? What is recurring in these conditional statements? It's this relationship between the truth sets. And it really just helped me to totally reformulate the logic away from the truth table account of what a conditional means to this one that was a lot more. And so they taught me, I guess, is the short way to say it. I should also say, though, that as you make the statements more complicated, the analogies for them break down. And so you have to continue to help them generalize their ability to see more and more complicated statements as the same. That doesn't stop, actually. I mean, one of the big things about it is that as you change the statements, the form of the statements, students are sensitive to that change, and we have to help them make more and more complicated theorems still have the sameness for logic to apply. And there's a lot to be unpacked there. I'm not going to say I've exhausted that problem at all. Yeah.
So, Paul, I have two questions for you. One is, when are you going to write Peppa?
Peppa, yep.
Peppa Pig's book on logic? Two, I'm just curious, what's your take on how, like Hammock or any of these guys, like what do you feel like is the key difference between how you're thinking about things and how those books are, I guess, expecting students to think about logic?
I think one of the core concepts that operates at the heart of how we think about proving and logic and just so much of advanced math is the idea of implication and maybe inference. And if you just stop and think, what mental acts of mine are inferences or implications? And at what point do I expect a student to think about their own mathematical reasoning midstream and to recognize I just drew an inference and I made an implication? And it's like we're going to, we have this one way to describe most every mental act in advanced math, if it's deductive or if it's always true. And I don't know where students are going to, I don't, that's just such a weird abstraction. And so we have this path metaphor from hypotheses to conclusions that sort of hides the psychological structure that we're sort of referring to there. And I think after we tend to teach students for a while, they kind of often probably pick up on the game that we have this kind of directed sequence of steps towards something, and they just kind of get, but I also think it's this huge bit of the hidden curriculum that we don't coherently talk about, we don't coherently invite them into, we don't have good ways to help them really build a notion of an inference or an implication as we think of it. And without that, without trying to hide that in what I'm doing, I had to say, well, what else can we do? And so this notion of reference and set structure was a way for me to feel like I'm being honest in what I invite them into making sense about without just kind of hiding all that psychology that really is frankly doing a lot of the work that's embedded in a lot of standard mathematics texts. There's probably more I could say, but if there's like one big thing, I'm just like, when are students going to pick up on this idea of an inference or an implication? And then, think of that as a single thing that in all of math, that's what I'm doing. All proofs entail a sequence of inferences. And then to like reflectively apply that to their own reasoning as they do it. It's just, maybe it's not as big of a problem as it seems to me in my head, but I'm still stymied by that. It really bothers me, to be honest, to student experience, yeah. So there's a lot with this. I don't know that I'm right. I'm doing what makes sense to me in the design work, and that's a big motivating factor for me.
So just really quickly, a question from sort of the virtual side. Praveen Chakara wants to know, he's thanking you for your wonderful presentation, and he's saying, I wonder if you identify any compatibility or dissonance in students' language with logic in relation to their understanding of order of quantifiers and mathematical statements.
Yeah. So order of quantifiers, I was teaching that just this week in my intro to proof class. This is a really, this is a great instance where there's just so much that we hide that the order, you can rearrange the statement with all the exact same words in it, just change the order, and all of a sudden we're like, oh, totally different thing. And how do we coherently want students to build those images? I find that actually so in a lot of the literature, it seems to say that students, can't struggle with the kind of back and forth. I find if you give students statements that are tractable, they can piece apart that there are two different meanings there. And then once you recognize there's two ways to read, like if you permute the two quantifiers, there's kind of two possible readings, then they may understand, well, we kind of want to attach one meaning to one statement and one to the other. Like we need different sets of words to capture these two different ideas. But the real thing is then, well, how do we capture what are the two different ideas? And I've really just been using these diagrams. Once again, it refers to states of affairs. And there's the one state of affairs is as one of the things varies, the other one varies with it. So we have kind of pair off. Or the other state of affairs is one is fixed and cannot vary, and it pairs with all the others. And those are the two pictures. And at some point we just say, okay, well, those are both viable ways to think about pairing these objects. The statement may either be true or false based on which one we mean, so we probably want the language we want to be clear about which set of words refers to which state of affairs, and we just come to an agreement about which way to do it. And students find that pretty tractable, actually. What's a lot harder is why one of those negates the other, but I won't go there yet.
That's very nice, Paul. Is more or less on track, but there's somebody called Grice and Gricean implicature. And for example, to say for some, and we allow all when we say for some, but he says in ordinary language, why would we say for some if there are any exceptions? Because that's not how we talk. And so there's stuff out there that we might refer to. This is not quite conditionals, this is quantifiers.
Yeah.
But about so math language is just different. It's a restricted set. We don't capture what everyday language captures.
I think, though, so there's 2 points on that. And I think Grice's stuff is huge. I mean, you can especially apply Grice's stuff to say, why do students not like 15 is even or 15 is odd? Because often, if I say or, I'm conveying uncertainty often. Like if I tell you, hey, tonight at dinner I'm going to have the fish or the chicken, but secretly, I've already decided I'm having the chicken. Well, that'd be a super weird way to talk. And you're like, why don't you want to tell me what you're eating? Like, that's very strange. So, and in math, so when we ask true or false, we're not asking, is this the best or most informative statement I could give you on the subject? In math, we expect students to know we're simply asking, does it accurately describe the state of affairs or inaccurately describe the state of affairs? But students often read the sentence to say, is that a legitimate speech act? Is that how I would talk if I wanted to really communicate with you? And quite often the answer is no. Tons of the statements in logic texts are not helpful or useful or interesting, relevant sentences. And so, that's a great lens under which to view why I'm railing against the status quo. Yeah.
Hi, Paul. I just wanted to wonder, as someone who's teaching discrete math now to 250 CS majors, I was interested in your example because it seemed to see your CS major had insights that particularly I'm guessing your math major didn't. And I'm wondering if you followed up on that as to why. For instance, another place where the truth tables come into play, where the CS majors I found tend to have advantage of the math majors, is why P implies Q would be true if P is false.
Yeah.
Right.
Yeah. So let me say a couple things on that. First off, actually, both April and Mariah were both CS majors. And they both were, so that wasn't the only distinction between them. But I'll say also the way I am reformulating logic is logic for the purpose of getting to proof-based math. I think actually folks in discrete and CS may need some other ways to think about logic that are actually not quantified the way I tend to do it. And I want to be honest in saying that's actually a limitation on what I'm doing. And I want to continue to partner with more computer scientists and discrete folks to learn about what are the limitations to the ways I'm reformulating things. But to your point, if the whole why is the conditional true and the antecedents false? If you just talk about subsets, that just doesn't come up. Because we know, what is the sentence saying? It's saying the if set's a subset of the then set. And they go, okay, we agree with that. And they know that numbers or things not in the if set don't interrupt that. They just are irrelevant. And they don't worry about it. But if you do want to argue to them, why do they want to say that it's true in that case? One of the arguments I give is for a lot of students, when I say if x is a multiple of 6, that whole sentence is only about multiples of 6. Again, the whole point of states of affairs. So I let them think that for a while and agree with that and don't push it until we show contrapositive equivalence. And then we say, wait a second, so this statement that all the multiples of 6 are multiples of 3 tells me that all the non-multiples of 3 are not multiples of 6. And so now it's no longer tenable to say that the sentence is only about multiples of 6 because it gave me new information about the non-multiples of 3. And that I've found students hate less than all the other justifications. So, yeah.
Just a question from the online. Igor had a follow-up to an earlier question. So if language is so important, he wonders how the things you talked about are English-driven. Does the literature from other countries identify same or similar issues?
Great question. My expectation would be the notion of if has some instantiation, and I think probably most all languages. It may have different flavors, but do I think language refers to states of affairs in all languages? I would infer, yeah. I mean, again, and this is like an overgeneralization. I mean, this is a useful guideline about how language works for students who are just beginning intro to proof. I should really say that's a better way to qualify my claim. And I would think that that basic tenet would probably apply in most linguistic settings. Are there different challenges to how this works, how not works, how we think about negating conjunctions and disjunctions? I'm sure there are so many complications I'm utterly unaware of, and blissfully so. So there's a ton to be explored, and it's fun. The big deal for me, though, is in any language, what's the trick? Invite students to engage in the language, to compare the language, and for themselves to think about their own, how the language refers for them. And I think you could do that in any language, and probably you'd get some really productive conversation, and students would make some really neat insights. So that's the easy trick that you can apply anytime, anywhere. So yeah.
Thank you, Paul. Sorry, that was a big build up there.